So the aromatic substitution reactions that we've looked at in Chapter 24 and Chapter 25 so far have proceeded by mechanisms involving an aromatic ring attacking an electrophile. That's why we call it an electrophilic aromatic substitution reaction. But in this section, we're going to switch gears a little bit and we're going to look at nucleophilic aromatic substitution reactions. And in these reactions, the aromatic ring is attacked by a nucleophile. Now we're going to explore two types of these reactions, one that proceeds by a nucleophilic addition-elimination mechanism, and the other by an elimination nucleophilic addition mechanism. So nucleophilic aromatic substitution reactions are fundamentally different from electrophilic aromatic substitution reactions, but nucleophilic aromatic substitution reactions are presented here because they can be used in synthesis in conjunction with or an alternative to electrophilic aromatic substitution reactions. Okay, and so that's why we're fitting them in here within this chapter. So, for example, when 1-chloro-2-nitrobenzene, shown here, is treated with excess ethanamine, shown here, N-ethyl 2-nitroaniline is produced. And so what we see here is that overall, the chlorine is replaced by an ethyl amino group. Now, the mechanism for this, which we're going to show right here, so we're going to start with all our mechanisms. We're going to draw the reactants first. All right, so the carbon that's bonded to the chlorine is relatively electron poor, okay, because chlorine is going to withdraw that electron density. And what we find here is that this H2N is going to act as the nucleophile, and so it's going to come right in here and attack that partially positive carbon atom. When it does that, these electrons are going to jump right there onto that carbon atom of the ring. And so this first step is a nucleophilic addition. Now I'm just going to follow my arrows to form the bonds. And so when I do this, I'm going to draw my ring. Okay, I have my chlorine here. It has not left. Right, and then over here I have my nitrogen with 2 hydrogen atoms, and now it has 4 bonds, so it has a positive charge. We have our double bonds here, and then here we have an NO2, right? And we have 2 electrons here. Now, this is resonance stabilized. There are other resonance structures, and you can draw that if you would like some additional practice. When we go through and look at this, sometimes this is called a Meisenheimer complex. Okay, so this complex right here is a Meisenheimer complex. Okay, and it is especially stabilized by the NO2 group that's attached to the carbon atom. It's pretty electron withdrawing, right? So this is going to withdraw some electron density and stabilize this atom here. So in the next step, what we're going to see is a proton transfer. Where these electrons are going to come, they're going to grab that proton. Then these electrons are going to go on the nitrogen there. At this stage, we're going to form this molecule. Right? And then we also have this molecule formed as well. Now this is going to go through a nucleophilic elimination reaction where these electrons are going to come here and they're going to reestablish that aromaticity, and then that chlorine is going to leave. And so there is our product. So let's talk a little bit more about that Meisenheimer complex that I threw out there for just a second, and I mentioned there are some other resonance structures. So here's the Meisenheimer complex, and so this step 1 is really assisted by the resonance delocalization of the negative charge of the intermediate. When we look at this, it's important to remember that not every nucleophilic aromatic substitution is feasible. But nucleophilic aromatic substitutions that proceed through the Meisenheimer complex generally require at least one moderately or strongly electron withdrawing group, ortho or para to the leaving group. And so notice that this is the case that we see with the previous reaction. And we can see how these resonance structures help stabilize this charge through the additional resonance structures here. So the Meisenheimer complex is really important to this particular reaction. Now, the location and number of strongly withdrawing electron withdrawing groups relative to the leaving group is also shown in the reaction here. This is a substitution. It's similar to the previous one we looked at, and this reaction also requires less heat because the leaving group here is ortho. Sorry, let me find it. The leaving group here is ortho to one NO2 and para to the other NO2. So remember, when we talk about ortho and para, OMP is the way I remember that. Ortho, meta, para, right? And so ortho, meta, para. And so less conditions are required here because we have multiple electron withdrawing groups that help stabilize that intermediate complex. Now, nucleophilic aromatic substitutions can be carried out with quite a few leaving groups, even F-, which is what we see here. The major restriction is that the leaving group needs to be more stable than the incoming nucleophile. So the leaving group needs to be more stable. And we remember that when we say more stable, what we actually mean is less basic, right, than the incoming nucleophile, right? Because that more stable of the two will depart in the elimination step. Even without a strongly electron withdrawing group attached to the ring, a halobenzene can still undergo nucleophilic substitution. So for example, chlorobenzene here can react with sodium hydroxide to produce phenol, or it can react with a potassium amide to produce aniline, shown here. These reactions typically require really extreme conditions, and like, for example, like a strong base or high temperatures, or both. And so that doesn't always the best reaction to do necessarily. Let's talk a little bit more about why these reaction conditions are required by looking at the mechanism. So in the very first step, what we're going to see here is a base comes in and it removes that proton in a proton transfer reaction. When this happens, right, this hydrogen's going to come in, it's going to remove that proton, and those electrons are going to go right there on the carbon. And so the next step is a nucleophilic elimination reaction. Where these electrons are going to go here, and this is going to be the leaving group, that chlorine. Now, this forms a benzyne intermediate. Okay, and this is very, very unstable. Okay, so the next step here is going to be a nucleophilic addition. Where the base, the OH minus, is going to come in again, right, and it's going to attack right here. Okay, when it does that, those electrons are going to go right there. Now, okay, this is going to undergo a proton transfer. Okay, where these electrons are going to come out, they're going to grab a proton. The electrons that make up the oxygen hydrogen bond are going to go back on that oxygen. And so what we see happening here is that we're going to go through another proton transfer where we're going to grab that proton there, and those electrons are going to go back on the oxygen. When that happens, we form this guy here, which then will go through another proton transfer, because now we're going to do an acid workup. So we're going to add here, and then we finally come down here and end up with our OH, our phenol there. And so this is the mechanism. So a few things here. Both steps 1 and 2 here and here are relatively slow. Step 1 is slow because a very unstable carbanion is produced, which is why that strong base is required. And then step 2 is slow because this benzyne product here is really unstable due to the large amount of angle strain caused by the triple bond. And so let's visualize that a little bit more. So remember, when we do mechanisms, these are all backed up by experiments. And one of the ways that we can do experiments is to use a atom that that we can track in the NMR in a little bit different way. And so these experiments were done with carbon-14. So the ideal bond angle for a triply bonded carbon is 180, okay? But the constraints of this ring require it to be about 120, and that has a really major effect on the strength of the pi bond that's in the plane of the ring. So we can kind of see this here. We have some really poor pi overlap. These p orbitals that are adjacent are normally parallel in a pi bond, but here they're about 60 degrees apart. And so that's what makes the overlap here so poor, as well as making the pi bond really abnormally weak and benzyne highly reactive. So because benzene is so highly reactive, it hasn't been isolated or purified, though a lot of experiments indirectly support its existence. And the most kind of compelling argument or experiment is the carbon 14 labeling experiment, where this molecules was synthesized, where we have carbon 14 specifically here, and the chlorine is bonded to the carbon 14. When it reacts with KNH2, it produces roughly equal mixtures of two isomers of aniline, where the NH2 group is bonded to the carbon 14 and then in one isomer, and a carbon 12 in the other isomer. These results are consistent with benzene's symmetry around that triple bond. So that nucleophilic addition to benzene occurs with essentially equal likelihood at both alkyne carbon atoms. So basically what we're saying is, look, because one NH2 is attached to this carbon 14 is inherently different. This is a carbon 12, right? Because we get two isomers here and we get equal amounts, it supports the idea that this is a triple bond that's pretty reactive, because it reacts equally either at this side or this side of the triple bond. And so that's why benzene is supported as one of the steps in the mechanism. So, we are also going to talk about some organic synthesis in this chapter and considering regioselectivity and attaching of groups in the correct order. So when we think about planning syntheses, I want you to remember that a substituent that's already on an aromatic ring is really going to influence the site of reaction in subsequent electrophilic aromatic substitutions. And so in a synthesis that requires multiple substitutions, we need to choose wisely the order where we need to carry this out. So look at this. For example, you want to synthesize M-chloronitrobenzene from benzene. How do we need to go about doing that? Now, benzene can be nitrated by treating it with concentrated HNO3 in sulfuric acid, and it can be chlorinated with Cl2 in the presence of FeCl3. So those are the two syntheses that we're going to kind of think about, but the question is, which order, right? Should we do the nitration and a chlorination, or chlorination and nitration? Well, when we look at this, what we're trying to do here are to get these substituted in such a way that they have one carbon in between them, right? So if chlorination takes place first, we are going to encounter a problem with our regiochemistry. So chlorine here is an orthopara director. So if we were to come here and do a nitration, that's going to yield the major products as O-chloronitrobenzene and P-chloronitrobenzene. But our target, right, was the M-nitrochlorobenzene with one carbon in between the two. So this order doesn't work. However, if we come here and carry out the nitration first, which is a meta-director, and then the Cl2 next, that it will give us M-chloronitrobenzene, which is what we're trying to synthesize. So let's look at another example. This is the synthesis of M-nitroacetophenone, okay? Now, the order, as we mentioned, in which substitutions are carried out can also be an issue, because some substituents on the ring make certain electrophilic aromatic substitution reactions unfeasible. So remember when I made a big deal about the Friedel-Crafts acylation? These do not occur with moderately or highly deactivated rings. That was in section 25. So we need to avoid placing these kinds of deactivating groups on rings prior to carrying out the Friedel-Crafts reaction. So when we look at this synthesis then, it requires two substituents, a nitration and a Friedel-Crafts acylation. because the NO2 group and both the acetyl group are meta-directors, regiochemistry does not depend on the order where these substitutions are carried out. So, right, when we look at this, though, we need to avoid the Friedel-Crafts reaction, though, on the nitrobenzene, because the benzene ring would be highly deactivated by the nitro group, and Friedel-Crafts reactions don't work. So instead, we should do the Friedel-Crafts reaction first, the acylation, and then the nitration for this reaction to go smoothly. So let's do an example. How would you synthesize p-isopropyl nitrobenzene from benzene? And so when I do this, the very first thing I ask myself is, okay, what substituents am I dealing with, and are they meta or para directors? So my first substituent here is NO2, right? And this is a meta director. So this is a meta director. So that means as a meta director, OMP, it's going to go either here, right? Oh, let me go back. Okay, sorry, I got distracted. Out of order. So that's a meta director, okay? And then the next thing I look at is the isopropyl group here, right? So there's my isopropyl group, and I ask myself, okay, what type of director is this? When we talk about the isopropyl group, right, that's an R group, and so that's going to be an ortho para director, okay, because that's just the generic kind of R group there. Now, both groups are attached by an atom that has no lone pairs of electrons, okay, and the NO2 group is electron withdrawing while the isopropyl group is electron donating. So just some things to kind of keep in mind. The target here is a para isomer, okay? And so what we need to do then is add the ortho-para director first. So we're going to come here and say, okay, I'm trying to get something that is para. So from benzene, I am going to come here and I am going to, that's Cl and AlCl3, so Friedel-Crafts alkylation, and I am going to add that first. And knowing that that's an ortho-para director, then I'm going to come here and say, okay, hey, look, ortho, meta, para. Now, when I add this HNO3 with H2SO4, that will add in the para position. Now, it'll also add in the ortho position, but what we're really asked for here is the para, so that's all we're going to show. Okay. Now, if these two substituents here were meta to each other, right? If the NO2 was here, then I would add the meta director first and the ortho-para director last. So basically what you want to do is you need to analyze, are these ortho-para or meta to each other? If they are ortho-para, add the ortho-para director first. If they are meta to each other, add the meta director first.